Line A6, we're in Learning Task 2, where we're going to go and talk about rectifier filters. Now, there's two main types of filters, and the book doesn't really give us much clarity between the difference of those two, but we are either trying to go and filter out stuff, so we're going to go and have what we refer to as frequency filters, which are also going to be built out of, RLC type of circuits. It's going to be inductors, capacitors that we're going to go and use. And what they're going to do is they're going to go and either pass certain types of frequencies or they're going to go and block certain types of frequency. But it's going to be frequency dependent, where they're going to be able to, as AC, pass only certain values through there. A frequency filter is always going to go and be an AC value that it is going to be looking for. What we're looking at over here is we are looking more at what is called regulation. They talk about this thing as a filter, and it is considered to be a filter type, but what this whole thing is really more to do with is to do with voltage regulation. I'm just going to go and cross it out over there and write that in. Because a voltage filter is completely different than a frequency filter. So when you're trying to look up stuff, sort out questions that you might have, as soon as you go online and you start typing in, frequency, or sorry, not frequency, but filtering, you're going to get usually bombarded with frequency filtering answers and, circuits and things like that, because that's the most predominant type of filtering that we have. This over here would be more along the lines of a voltage regulation type of circuit. So that's just a point of clarity going into there. Know what you're looking at as you're looking at components. Okay, we're going to go talk about regulation on a single-phase half-wave rectified circuit over here. Because we know that if we don't do this rectification on this circuit over here, and we'll just white out this capacitor inside of there, if we leave the circuit as is over here, what we would get out of it is we are going to go and get out a hump and a line, a hump and a line, and a hump and a line. And it just continues on like that. What this does is it provides a rather erratic operation for any type of a load, because it's going to get a burst of power and then nothing. It kind of has to coast its way through and get a burst of power and then nothing and coast its way through. It can be really hard on equipment, and it can lead to, once again, erratic operations on those pieces of equipment. What we end up doing is we end up placing a cap across there. And what is this cap going to do? Well, you got to think, first of all, which side of the circuit is the cap on? Take a look at where that diode is. On this side over here is an AC circuit. Everything on that side is AC. It sees both sides of the waveform. On this side over here, it is going to be DC. So we have to treat it as, what does a capacitor do inside of DC? In AC, what we just went through, a couple of weeks ago when we were looking at RLC circuits, we talked about how my caps could go and have things like XC on this side, and they would give us things like a leading power factor, leading VARs, and power factor and things like that. That was all AC things that we had for capacitors. But because our capacitors downstream on this side, it's going to be DC. And inside of DC, what does a capacitor do? It charges, right? We can go back into the stuff we looked at in the very beginning, your A1 line, and you can take a look at all these charging curves that we see for capacitors that are being placed inside of DC. So we can charge up a cap inside of DC, and then we can go and discharge it as well, right? And you should remember that if I have got an applied value of voltage, we'll just draw it here as voltage, on a regular DC circuit. So if I were to go and apply, this is my value of voltage that I'm going to have up here, and I've got no voltage, no voltage, no voltage, and then all of a sudden I turn on the circuit, close that switch, so that my voltage rises like that. What my cap is going to do is it is going to go and rise its value of voltage. It takes place over top of those 5 tau that we are going to go and have over there. And then as long as the voltage is up there, it's going to go and maintain it up there. It's opposing the change in voltage. See how the voltage went from 0 to full? This thing opposed that. It slowed down that rate of rise. Same as when my voltage is actually going to go and drop over here. My cap at that point is going to go and oppose that change. My voltage, so my cap was charged up. My voltage goes from high to low. My cap is going to go from high to low as well, but it slows down that drop that we are going to have. We're going to use that same sort of action, that DC action of charging and discharging, but we're now going to go and deal with it on a different type of DC, that's half-wave rectified DC. Okay, looking at this one over here, what's going to happen on the DC side, and I'll remove that big nasty line there in a second, is that we're going to charge up this cap, and then this cap is going to be able to go and discharge based upon wherever the greater amount of volts are going to be inside the circuit, either from the AC input or that's going to come through the rectification or from the cap itself. So let me just erase all of this so that we can see what's going on again. Let's start with taking a look at our diode. Our diode is only going to go and be forward biased if I have got a negative here, which would mean that the opposite side would have to be a positive. So the only time that I'm going to go and have current passing through here is when I've got a positive here and a negative here. Which means that, we'll start with this one right now, the second that I go and turn this circuit on over here, the AC side, I'm going to, and we'll take a look just at the negative one here, I'm going to go and have current that is going to go and drive through. We'll use this red line here to drive through my current that is going to go through the load and back. We see that that current is traveling through in this direction over here. I am also, at the same instant, going to go and have electrons. This over here is a negative. So I'm going to go and drive electrons in. Those electrons are going to drive into this circuit over here. They're going to start to build up on this plate. As they build up, for every action, there's an equal and opposite reaction. They're going to drive electrons away on this plate over here. And then those electrons are going to get driven back out to the source. What happens is that we see a charge building. Remember that V is equal to my Q over top of C, the number of coulombs that I'm holding on that capacitor that I'm going to have. So this is what's happening inside of here when my voltage looks like that. We're charging up that cap. Then when my AC alternates, so now we're going to go to a positive here and a negative here, so that's my alternation voltage, we are going to go and change characteristics. Let's start by taking a look at this diode. Is it going to be forward biased? No, we've got a positive over to the cathode, so this diode is now going to go and be blocking, which means that it is no longer going to be supplying current to the load through there. It is also no longer going to be supplying a charging current to this cap, so we can remove that over there. But this cap does have a voltage potential across it, right? It's going to go and have all these electrons on this side, all these holes on the other. What does nature tend to want to do? It wants to go and balance, right? So we are going to go and see these electrons that are then going to go and leave from here and travel, check out that arrowhead, it's in the same direction, travel through here as they go back to fill the holes on the opposite side over here. What we are getting out of this circuit right over here is a discharge off of my cap. What does a discharge curve look like? It's going to be a droopy curve, looking like that over there. And how long is it going to take to discharge? Well, that's all going to be based upon the number of electrons that I'm going to store, so that's going to be my capacitor charge, and the resistance, how hard it is for me to go and migrate those electrons from one side all the way back out to the other. So this is going to be my AC filter. On the next alternation, this is going to be, so right now on this alternation, we would be losing some of these holes. My voltage is going to be going down because I'm starting to take electrons from this side. As I'm passing them through to the other side, those electrons are filling the holes here. And so I've got less potential difference across here, which means that the voltage itself is sagging. Then my AC alternates. When my AC alternates, we go back to having our negative here and our positive over here. This would once again turn on, and at that point, the source would take over supplying the load current, and my cap no longer would be doing that. My cap would be taking in electrons to go and start recharging over here and driving them away on the opposite side. And it just completes or continues to do this cycle, time and time and time again. What we get out of it is we get a curve that's going to go and look like this. What we're really looking at on each one of these, if you were to split one of these in half over here, is you are going to be looking at a charging curve, and then you're going to be looking at a discharging curve. Now, it's fairly flat. It actually does a little bit of a sag like that as it's coming across over there. But it is very, very, very much going to be, these same RC types of curves is what we were looking at when we were dealing with DC capacitance. These are going to be affected by the load resistance. If I've got a very low value of resistance, okay, so just write that in over there, low ohms. That low amount of ohms means that I'm going to be really quickly able to discharge that cap through here, which means that my voltage is going to go and sag down fairly significantly. It would look like that. If I went to a high value of ohms, we'll say high, what's going to happen is it's going to take a long time. I'm just going to get a trickle of electrons that are going to be going through here, which means that my voltage would then stay more or less constant, and it only has a little one there. And so what we start to do is we start to change the amount of ripple that we are going to see off of this. They do give us a couple of drawings. We'll look at this one first. We'll go back to the other one in a second there. But this is just showing what we just talked about over there. That if I have got a low current load, and I want you to be, very intentional about when you look at when it is current. This does not mean it is a low resistance. Obviously, if it's going to be low current, it must be high resistance, right? High resistance for that value of voltage that we get stored on the cap would mean low current. Same with if it's going to be high current, it would have to be a low resistance. Remember that load on an electrical circuit is always, always, always going to be the current that that electrical circuit is pulling through there. And that's defined by the resistance that we have on there. What we're seeing when I've got a low resistance or a high current load is that I'm going to get a fairly large value of ripple voltage over here. That ripple voltage is, not necessarily going to be great for my system. It's going to provide a bit of erratic operation. It's not terrible. It's not as bad as, what it could have been if this thing was going to be that half wave rectified, but we see that we're starting to get down close to it. We would be far better to go and have, a low amount of ripple. And there's only a couple ways that we can go and create low amount of ripple. One would be to have a high resistance load, but that's not always practical. Sometimes we actually need to have a low resistance load. The only way that we can go and get less ripple out then would be for us to go and get a bigger cap. Okay, we'll just draw a bigger cap. That bigger cap would then allow us to go and store more electrons on it, which would mean that we would be able to go and maintain that voltage for a longer amount of time. The problem with the bigger cap is that we get massive amounts of inrush during that charging, and it can sometimes be enough that it's actually going to go and trip out some of my load protection over here. The other drawing that was previous to this one over here that had tau is equal to RC, is a little bit of a difficult drawing to understand. What they aren't showing is the actual RC curve. They're saying that the RC defines how much we're going to go and sag away, which is true, but they have drawn it poorly. This is not what it looks like. The RC for this circuit would actually be, the tau would be 5 tau, would be how long it takes for this thing to go and sag all the way down to 0. So if I did not have the subsequent humps coming through over here, right, the rectified, if I shut that off, this over here is going to be my curve. Now, it's a really stretched out curve. It is this same curve. It's just been stretched out longer over here, but eventually that gets all the way down to here. That RC that they're looking at over here is 1 out of the 5 RCs that we're going to have along. I know I only drew 4 there. It's because I'm not very good at eyeballing the size of these things always, but that's what they're trying to go and show off. So it's just a poor one. I wouldn't spend a lot of stress trying to, understand what they're doing on here because it doesn't actually make sense. They're trying to show that there's a relationship between the RC and how much it sags. And that is correct. It's just not the right way to draw that. We do call this over here voltage regulation. Voltage regulation is just going to be the change in my voltage level with the load. Now, there is going to be an average value of voltage that we will take off of these, right? Because the average is going to be between my top of my peaks and the bottoms over here. So for this one over here, I'm going to go and have a V average that is going to be just, if you take a look there, it is right a little bit above here, and it is a bit below there. So it's at a high average value. I'm going to carry that across to this one over here. This one over here, because my ripple is bigger, the peaks and the drops, my average is going to sit lower down. So if I look at this average value, I see that it's down about here. And I can see that I maintain a higher average voltage off of this one over here, the one where I've got a low current growth load. That is going to be termed as being my voltage regulation. The top one would have what we refer to as good voltage regulation. The bottom one over here is going to go and be bad voltage regulation here. The caps that we will utilize inside of these are usually going to be electrolytic capacitors. Electrolytic capacitors are really easy to manufacture. Remember, it's going to be that aluminum oxide that we're building up on them. We covered that at the very beginning of this year. And they're going to be a polarized type of capacitor. We identify which leg is going to go and be the negative leg because it's going to be the short leg, right? It would be a negative thing if your leg got chopped off. So we term that as being our negative leg to these capacitors. They'll also otherwise sometimes have a white stripe down the side of the capacitor, or they're going to go and have a set of like positive, negative, plus, minus mark. Those are going to be on them as well. You do need to go and make sure that you follow polarity. An electrolytic capacitor cannot be connected in reverse, because what happens then is we're going to reverse the oxidization. So we're going to go and strip away the oxidization, then have to rebuild it in the opposite direction. In what we would do by applying it to 120 volts or whatever our system voltage would be way too fast, and it would end up blowing up. You would have to do that slowly, that you'd strip it away and then build it on the other one so you wouldn't overheat them. But just directly reverse connecting them in, it's too fast and the thing just grenades. Let's talk about our PIV ratings that we are going to have. What is PIV? Well, PIV is going to go and be my peak inverse value of voltage that I'm going to go and have. What PIV are we talking about over here? Well, we're talking about the PIV of the diode. Both of these have got PIVs. This one has a PIV. This one over here is going to go and have a PIV. It is a standard rating on electronic discrete components, the peak inverse voltage or the maximum backwards voltage we could place across it. But if we take a look at this one over here, does it ever get backwards voltage? Well, once again, let's draw that line, and we're going to say we got AC here, we have got DC over here. If we take a look at that, we see that the DC side is where this thing is living on, so no, it's not going to get anything that it's going to go and be backwards to. It has already that protection of that diode that's upstream of it. So we don't need to worry as much about the DC side over here for that cap. What we do need to worry about is we need to worry about this diode that we are going to go and have over here. Because this diode is going to go and see a differing value of voltage. Let's go and take a look at our cap over here. Let's go and start, before we do this, let's just start by making this the opposite polarity. I want to start with this circuit over here as being negative and positive. What happens when the circuit is negative and positive? Well, we would be forward biased on this, right? We have negative to the cathode, so this is forward biased. So I'm going to go and have a peak value of voltage that is going to be, 170 volts in this direction. We're going to say, okay, we have 120 waveform. So right now we're going to go and have 170 volts. That 170 volts is going to cause current to flow, some of which is going through to the load, and some of which is going through to this cap that is going to start building electrons. So we're going to build those electrons over here, driving electrons away from the opposite side, resulting in holes. Those electrons leave the circuit over there. So we will go and have, at this point, we can charge this thing up. How high? Well, we're going to charge it all the way up to 170 volts that we would have. Right? That's what our peak is, so that's what we would be able to charge it up to. So this is going to become 170 volts. But then what happens is that this is going to go in reverse, right? We now are going to go and have our positive up here. It's AC, it's alternating, negative down there, and so now we're going to have 170 in the opposite direction compared to this one over here. So if we take a look at this, and that's what this one over here is showing, this over here would be where the resistor is. This is my AC supply, but we're freezing time and treating it as if it were DC. What we're seeing over here is that when my AC is in the opposite direction, see how that positive over there lines up with this positive over here? And when my cap has charged up, that's positive and that negative that we see over there, we're going to treat that as if it were a DC supply, a battery over here. What we would see is that there's connection between there, so it's as if we have got 170 here and 170 here, and as if this thing is bridging across that gap there. So it's going to have to be double the peak that we are going to go and have. Twice the peak value of our AC input. Remember that when we have got unfiltered half-wave rectification, so I'll just take that out over there. If I had unfiltered AC rectification, this thing would need to only have a PIV of 1x, 1 times the peak. But as soon as we apply in this capacitor, which is going to be storing charge for us, we then have to go and change that to 2 components, twice the peak that we are going to go and need here. 1 component, single peak. 2 components, twice the peak that we need for these half-wave rectified circuits. When you are working on these circuits, there's once again going to be that little safety blurb that they put out about making sure you discharge them. Caps hold values of voltage. we see that, when we do hold this value of voltage, it should discharge through this. But if that's going to be a high impedance load, or if this is a load that has got a switch in line with it, that switch is open, that charge could stay stored on top of there, and you put yourself at risk if you start playing with that circuit. Be very careful with your capacitor circuits. Remember that for any of my low voltage caps, we got to be under 50 volts in 1 minute. And if it's a high voltage, we're allowed to take 5 minutes to get that thing down underneath there. If you are unsure, bleed them off. Don't short them off with a screwdriver shaft or anything like that, but make sure that you're using a proper high wattage, high ohmic value resistor. I do want to point out too, before we move on to the next filter, the L filter, that what we have over here, this type of filtering, works on this type of a circuit over here, a half-wave rectified circuit, where we are going to go and have, that hump in a line, hump in a line. It does also work on a full-wave rectified circuit. And if it's on a full-wave rectified circuit, we're actually going to go and have a much better voltage regulation, because we see that this peak over here picks that back up right over there, and it never gets down quite as low. So we will see caps that are going to go and be used on these ones as well, the full-wave rectified circuits. Okay, let's talk about inductor filters next. Once again, we need to first, before we start trying to figure this out, we need to define where in the circuit is this inductor. Let's draw that line over there. This side over here is AC. Once again, inside of AC, we would go and have things like XL, and we would have VARS L, VARS lagging, and we would also have power factor that would be lagging, etc. That's if my inductor were on the AC side. What is this side of the diode? This side is going to be my DC side, which means that I don't have all of that stuff. Instead, I'm going to go and have an inductor that is going to go and act as it would inside of a DC sine. What do we say an inductor opposes? It opposes any change in current that we are going to have. If the current is rising, it tries to slow it down. It says, hey, easy there. If the current is falling, it says, hey, get this back, in shape. And what it does is it collapses lines of flux back in on itself to go and boost that, right? So we've got that inductor on this side that is going to oppose any change in current that is going to go and happen. And it can do that by collapsing its own lines of flux in onto itself. We will call this type of filtering over here choke filtering that we are going to go and have. Because it does actually go and choke down the value of voltage that I'm going to go and have rising as well. Taking a look at this over here, if we go and give this thing a positive here and a negative value over here, we are going to then have this forward biased, so we can go and flow current through here. My inductor doesn't like it. It's going to go and oppose the flow of current, right? It's going to go and use its counter EMF to go and slow that down, so that what I'm going to get is I'm going to get a slower rise on my value of voltage. And so it's just going to slow down what we have happening inside of the circuit. Now, how does an inductor act in DC? We know that what an inductor does in DC is it starts out, the instant we turn it on, it's going to be dropping all the voltage across it, but then it drops itself out of the circuit until there's eventually no more voltage dropped across that inductor, right? It acts as if it were a short circuit at some point. These ones over here, what we're seeing on the graph is that this thing is slowing down the rate of rise. It never actually allows it to get all the way to a peak. But then when it does hit a peak and it starts falling again, then this thing is going to pick up and it's going to start dumping its lines of flux that it's got around itself back into that circuit to try to maintain them. So it slows the fall that we are going to have as well. What we get with these is we get a much more even type of filtering look to it. Compare, what we see over here for my output waveform, which is going to be this wobbly sort of line over here, with what we saw on this one, which was going to be a steep rise and a slow fall. A steep rise and a slow fall. These ones, it's the wrong one. These ones over here are going to be almost equivalent on the input side as well as on the output side. They also have got, the additional benefit that these things are going to be fairly robust. Capacitors do have problems with overvoltages, harmonics, and things like that. Inductors are just coils of wire. You insulate them well enough, coil them tight enough together, they're pretty much bulletproof. They're easy type of component to go and work with. So we'll use them on the DC side to go and filter stuff out. Now, both of them have got certain advantages and disadvantages. We are going to go and have some problems with our cap, that if we have got a load that is changing too much, our cap is going to go and change its voltage regulation, right? We see that dropping down over there. We also see that our cap is going to go and reach peaks. It's going to get up to higher values of voltage on my load, whereas my inductor is going to get to lower values. It never can actually reach the whole top peak there. So what we will do is we will sometimes go and combine both technologies together. We can go and have a cap, and we can go and have an inductor, and then we connect them either as a choke input or we connect them as a capacitor input. Really means which one of these is going to be first on the line. Choke input, we see that all of our current has to go in through the choke, through the reactor over there. That's why we call it choke input. Capacitor input, we see that all of our voltage hits the cap first before we go and take a look at the rest of the circuit over here. And then what they can do is they can go and aid each other. So this one over here, you got to remember that if I've got that rectified waveform, this is now going to go and change it into this gentler type of waveform over here. This over here is then going to charge up to those peaks, and it's going to discharge it. So what it's going to do is it's going to start taking out, it's going to start extending those peaks that we're going to have so that we get a much better regulated voltage. So it ends up being more along the lines of like a flat top, and then it kind of sags out, and then it comes into a flat top, and then sags out, etc. That's what we get out of our choke input. If we take a look at a capacitor input, the capacitor input will have to charge all the way up to our peak value of our voltage. But then when the cap discharges, it's going to run all its electrons off through this, so it's going to go and slow down the rate that we are going to go and have over here, our rise and our fall. Note that this inductor is always going to be in line with our load over here on this capacitor input. Right? If you take a look at that, whether we're feeding in from AC lines when we're forward biased on here, or whether we're feeding from the cap, that inductor is always going to be in line with this, and it's either going to be seeing this voltage or it's going to be seeing the source voltage, which are going to be the same. Smooth this one out here once again. Taking a look at your waveform over here of an LC filter, we see that our voltage regulation is going to be much better. Better voltage regulation means smaller voltage regulation. I'm talking about the top to the bottom that we are going to go and have over here. And by us combining both together, we really get additional energy storage, because that's all that caps and inductors are doing, is storing energy. This one has magnetism, this one has electrons, but if I've got a low ohmic resistance over here, rather than me dropping all of that down really quickly, I get to use the stored energy in both of these two components. There is one step better that you can go than this. That is going to go and be the pi filter, because it kind of looks like a pi. It's got that pi mark, not like a pie that you eat. You know what I mean, math pi, that one. These ones over here are going to be a capacitor on this side. This cap is going to go charge us up to higher values of voltage. This inductor that's over here is going to go and smooth down whatever we've got current coming in from my rectifier. And then this one over here is going to go and once again hold and smooth that. Remember how when we were looking at this, at this one over here, my choke input over there, that choke input had kind of a flat top and then a small sag and then a flat top and a small sag. Now my cap is basically going to go and fill that in. That's what we're seeing over here on that pi filter. Now, what we've gone through over here is going to go and be a really overly simplified setup of what filtering is. We're not doing values because we're not engineering any of these ones. What we're doing is we're looking for recognition. You have to, once again, out of your ITA, you need to be able to go and describe the different types of filtering that there are and how they go and react on a circuit. We're not going to go and create these as an engineered solution here. There are industries where you're expected to be able to go and do that. And even as an electrician, I know it might seem like, whoa, they're asking a lot of me as an electrician. Maybe, just don't go enter into the heavy industrial then if that's really not your forte. But yeah, you will have to go and make these calculations based upon the load. You cannot afford, for most customers, they can't afford to go and have an engineer calculate that, because engineers just charge out the nose, right? So if they have a change in their load, you know, they add another parallel branch. What's another parallel branch going to do? Well, you as an electrician know that if we add another parallel branch, my resistance is going to go down, the overall resistance of all of this, which would mean that my current is going to go up. And so when my current goes up, you know, you will have to make those calculations. The good thing is you seldom have to make those calculations on the fly, on the job site right there. You are able to go home, you know, and pull up the old Google machine, and then there are tons of web pages out there for filter design. Your biggest problem with creating these filters is going to be finding the correct type of filter to be using. Because what and we're going to say this one more time, what we generally see is that most filters, electrical filters, are going to be AC frequency filters that you're going to go and find online, because it's a bigger field with more problems, the AC frequency. This is going to be DC voltage regulation that we're trying to go and filter. So just be very clear which one you're going to be looking for. Okay, very last section over there, they talk about that the filter design considerations are always going to involve the allowable ripple. You should be familiar with that term, what ripple itself actually is. That's the peak to the bottom of whatever I'm seeing over here. This is going to be my ripple that they're showing there. I'm just going to go and erase all of that so we can see all these ones here. So allowable ripple, allowable regulation. So there's a big difference between regulation and ripple. I can have both of these be at the same values of voltage regulation, but I would have to take this to a higher peak and then this one to, you know, a lower low. You can go and average out, you know, to, well, if I take a look at this over here, what I could do is I could get an average value of voltage, this one that they're showing here, between this peak and between this drop. But I could get that same value of voltage between this drop and this peak over here. You know, I'd have to come up higher and drop lower, but I would still be able to get the same average value. This one, if I call that one, let's say that's 2 volts over here, and this one here is 2 volts as well, I could do it 2 different ways. This one over here has got this good allowable regulation, but it's got a smaller ripple. It would be considered superior to this one, which is achieving the same thing, getting me to the same voltage regulation, but it's doing so at the cost of a much higher ripple. Output voltage, you're going to need to design for rectifier peak current limits. That's going to be the maximum current that can go through the actual diodes upstream, and then your load current. The very last thing that I want to say on this whole subject of filtering is that the filters that are shown inside of here have been drawn in all these circuits attached to a half-wave rectified filter, because it's easiest to see the filtering difference on a half-wave rectified filter. However, what we are going to go and feed into this thing could be half-wave. It could also go and be full-wave. You know, and that full-wave could come off of either one of my 2 technologies that we've talked about, you know, off of either the bridge, or it could also go and come off of that biphase center tap that we were looking at. Beauty. That is the end of the filtering section. Okay, get yourself to the point where you can describe it and understand the basics of what's going on inside of there, and don't stress about trying to engineer the actual values so much that we are going to need.